one of the leading data scientists in the country when it comes to healthcare data, and someone who's been doing this for 3 decades now, is one of the lead advanced analytics professionals at Anthem Healthcare, Tim Gilchrist, to talk a little bit more about what's happening within this world of AI, machine learning, metaverse, et cetera. Hi, Tim. Thanks for joining us today and handing the virtual podium over to you.
Hi, Stan. Thanks so much for the intro. My screen, oh, there, it just came back. I want to share screen in a second, but exactly what Eric just said. We have to be really careful when it comes to how we handle adoption of AI. And I see, like Eric said, misuse of it everywhere. Nowhere is that more pertinent than ChatGPT. It's horribly inaccurate. It sucks up all the media coverage, and we need to be super careful applying it to healthcare. But there is another way, and I'm here to talk about that. What I want to do in this session is just go really quick through the history behind ChatGPT and another technology called BERT, which is superior for what we're trying to do in healthcare. Give you a demo and hopefully take some questions. So I'm going to share my screen. Okay. So there's something called BERT out there, and it's related to ChatGPT. For those of you that are wondering why there's a Muppet there, BERT was developed at Google, and they seem to have a thing for Muppets because the predecessor to BERT was Elmo. And I use this tool for population health. I'm not trying to use it for a very exacting tool to predict an individual that's good for a clinical study. That's not where it is yet. The reason why I'm talking about this today is it's a huge development in machine learning, solves a lot of problems for us, and has a lot of opportunity. So let's go really quick through why we're looking at tools like BERT, which is in essence a natural language processing tool. It's not your typical machine learning tool. So here we are today. We're drowning in data. Everybody knows these figures over on the left. We've got 71,000 procedure codes, 69,000 ICD-10 codes. I thought it was 92,000, but I looked it up and it was 69. 20,000 prescription drugs. And then on top of that, we have things like social determinants of health, where you live, what you eat, who your friends are, things like that. And then device streams from your iWatch, or if you're hooked up to some medical device. The chart on the right takes all that, and machine learning people know the famous curse of dimensionality. The more features you have, when you get past the dotted line that runs up the center, the lower the performance of your model will be until you hit 0 far out. This hurts us because we're constantly confronted with more and more instances of more and more data. And the typical ways of dealing with this are to remove data, as Eric said. You're controlling for people that are tall, or compressing the data. With PCA is a term it's one way to compress the dimensional space so your accuracy goes up. So that's where we are prior to things like BERT and ChatGPT. This slide is really just to give you an idea what NLP is, what it was before BERT came along. And if you get this, then you can start to understand what BERT is, or ChatGPT. So Word2Vec was the technology prior to BERT, and it is exactly what it means. You take a word, you turn it into a number, then the computer can understand where that word occurs in the sentence and what words occur near it. So if we use this example below, king is to man as woman is to queen. This is the famous NLP example. The blue arrows represent where you're measuring that cosine distance between words. and you start to form associations. In a large text like BERT, there are 768 vectors for each word. And the way I like to remember it is Inuit people have 50 words for snow. I don't have 50 words for snow. BERT has 768 dimensions for each word that it encounters. And it's even more complicated than that. At the end, you look at the formula at the bottom, you can take what was words, translate them into numbers, and say king minus man plus woman equals queen, which is that at that moment, the machine has a vague understanding of what those words mean, and you can manipulate them with math. So if you get that, we can move into BERT. It's just important to know that computers don't understand words, they understand numbers. So we're using representations of words that are called tokens or word embeddings to make sense of language. So here comes BERT. In 2018, Google develops BERT. The reason why I'm talking about it now is a lot of the models have only become public very recently. And we'll get to that in a minute. It's very expensive to create a BERT model. They're bidirectional, which is the big difference between ChatGPT and BERT, in that BERT can understand the position of a word in a sentence or a paragraph, and ChatGPT does not. In terms of data size, and this gets back to the curses of dimensionality we talked about, a BERT model can include the entire text of Wikipedia, the PubMed, or electronic medical records in a single model. It doesn't use columns and rows like most data, most machine learning applications, so you do away with the dimensionality problem for the most part. And the big example here, the really most important distinguishing characteristic between BERT and everything else is the concept of attention. BERT uses a special layer in its processing to attempt to understand the relationships between words, even when they're at a great distance. And this is very important when you're trying to discern between words that sound like other words, or what is the most important word in a sentence, like a diagnosis, or someone has a major medical event. BERT can pull out that term, that event, and make it more important than the surrounding words. The last two things are transfer learning. This one is huge, and I'm going to demonstrate this in a minute, where you can take something that someone else built, say Wikipedia, and then you can layer over that understandings or embeddings from medical data. And the two are merged, and they become greater than the sum of their parts. This is something you just can't do in typical machine learning. And then the transformer, which said simply, it lets processes run in parallel, doesn't take a lot of RAM. So you can do things like ingest Wikipedia. It just takes a long time. These are things that would blow up your typical model. So the demo, what we did is, so Google came out with BERT, and it's called BERT Base, which is basically Wikipedia, a bunch of books, things like that to understand human language. Then along came someone that did bioclinical BERT, which also includes PubMed articles and discharge summaries, about 1 million discharge summaries from hospitals in Massachusetts. So we combined that information with 7 million diagnosis combinations from patients. So here you're crossing a divide between research in PubMed and PMC, Wikipedia, and clinical data that comes out of a claim system. So let's see what that looks like. And Stan, let me know, keep me honest on the time.
Yep, you're good. Couple more minutes.
Okay, great. So I'm going to thrill you with some Python code. I wish I had it in a better setup right now for you, but this is Python. It's one of the leading languages out there. And what I've done is I've done that join between the PubMed, Wikipedia, and medical data. And I'm going to run a typical query. So hypertension, chronic back pain, hyperlipidemia. This is me on an everyday basis, right? So how are those words related? And then the mask token at the end tells the model to fill in the blank. What's the missing part? So I run that code and I come down here, and anxiety is what comes back. And if you look at the medical literature, those conditions are often associated with anxiety. So that's what we would expect. But what we can do different here is start to mix things. So let's ask it a question. What will artificial intelligence bring to healthcare? I mean, we're sitting on top of this enormous data set of PubMed and all these research papers. So let's see what it comes back with. Decisions comes back. And this isn't the machine drawing a conclusion. It's not using any sort of emotion. It's just saying that in all those millions of texts, the word decision is often closely associated with artificial intelligence and healthcare. And it can even understand words like bring to. So how does that modify the term artificial intelligence and healthcare? So now let's really cross the divide here and get into social determinants of health. So we're going to do food insecurity, someone with asthma, and their health access. And the reason why I'm doing this is, and it's not the best presentation. There are visualizations that are coming out every day. This is early days for this. The reason why I'm doing this is we're constantly asked to bridge the gap between clinical and non-clinical data, and it's very difficult to do. So let's do that. And barrier comes up. So let's interpret that. It's a barrier to health access. And that means that that word barrier is closely associated with people that have food insecurity, are sick, and are seeking health access. So those are some of the examples. I wanted to leave some time for questions. I hope I've described it pretty well, but we have any questions?
This is fantastic, Tim. And I think, you know, again, if we popped Tim's LinkedIn page into the chat box, if you could all just reach out to Tim directly on LinkedIn if you have any questions. And Tim, I think this is the first time that we've had this kind of a detailed data science talk at HITLAB and seen the number of people who actually are participating in the symposium go up. About 10%. I think we added about 10% more viewers to the hundreds of people tuning in from around the world. So well done on that. And again, thank you very much. It's just a tremendous presentation, and let's give Tim a virtual round of applause. Thank you, Tim.
Thanks.